Hello everyone and welcome to our webinar Unleashing Innovation with UCIe 3.0. We are going to explore the latest advancement in the Universal Chiplet Interconnect Express standard, focusing on what's new in the 3.0 specification. So let's start with the fundamentals. What is UCIe? The Universal Chiplet Interconnect Express is an open industry standard for on-package connectivity. It is designed to provide high bandwidth, low latency, and power efficient connectivity, which is critical to meeting the growing demand of compute, memory, and storage. We see this need across every segment, from the cloud and high performance computing all the way to automate and handheld devices. The most powerful concept behind UCIe is the ability to mix and match dies from different sources, different fabs, different designs, and even different packaging technologies, all in one system and package. It supports various protocols, data rates, and include key features like error detection and correction. To achieve this, UCIe defines three distinct packaging options. The first is we have the standard package or 2D. As you see in this diagram, this involves mounting the dies side by side on a traditional organic package substrate. This technology is optimized for a low cost and a longer reach, anywhere from 10 to 25 millimeters. It provides a massive improvement in signal integrity compared to off-package. The next is advanced package or 2.5D. This is all about performance. Here the channel reach is kept very short, less than 2 millimeters. This short, dense interconnect is optimized for maximum bandwidth and low latency and the best power efficiency characteristics. The diagrams show a few examples of this, such as using a silicon bridge like EMIB to connect the dies. And the third and the newest category is UCIe 3D. This moves the interconnect into the vertical dimensions. This technology uses a two-dimension array of bumps to transmit data from die stacked differently on top of each other. As this diagram shows, this uses advanced technologies like face-to-face hybrid bonding and TSVs. This 3D approach provides a path to even higher bandwidth and low power. Here is UCIe configuration. UCIe is also incredibly flexible in its configurations, like we have single module configuration for both advanced and standard packages. Here for advanced package, a single module is typically cross 64 or cross 32, and for standard package it's cross 16 and cross 8. This is scalable. You can implement multi-module configurations to aggregate 2 or 4 files for even higher bandwidths. Showing in this figure for 4 module or 2 advanced modules. And notably, UCIe also supports a sideband only configuration. This allows for a very low power control, like using a 1, 2 or 4 port sideband interfaces. This is a feature enhanced in new specification in 3.2. Alright, let's look inside the stack. UCIe is logically divided into 3 layers. The very first layer is protocol, then adapter, and then file layer. Here at the top, the protocol layer is responsible for mapping higher level protocols like PCIe, CXL, and other streaming protocols in the UCIe FLIT format. And in the middle, the die-to-die adapter provides the optimized data path. It handles the heavy lifting. It can do things like CRC computation, link state management, and parameter negotiation, and also retry mechanism. And here at the bottom we have file layer, which handles the actual signaling. It has two parts, the sideband and the mainband. The sideband, which is low speed and out of band channel, used for link training, configurations and management, and the mainband, which is high speed data path itself. These layers communicate over the sideband interfaces, the flit aware D2D interface between the protocol and adapter layer, and the raw D2D interface RDI is between the adapter and physical layer. So this is very detailed and important section. Let's take our time and walk through the different flit formats defined by the specification. The protocol layer is responsible for generating all types of flits. So the first format is row format. This is the simplest format, a 64-byte payload. It is mandatory for the streaming protocol and optional for others. The key feature here is that this mode is supported when retry is not required. So here the second format is 68-byte flit format. This format is mandatory for CXL 68-byte flit mode and PCI non-flit mode, and this is optional for streaming. It also supports retry, which is performed over this 68-byte flit. As this diagram shows, this format is pegged. It also defines a pause of data stream token, which is valuable size flit used when the transmitter has no data to send. Then show the detailed flit header definition for this format, both without and with retry. And the format 3 is standard 256-byte end header. This format is mandatory for PCI flit mode, and this is optional for streaming protocol. It's called end header because if you look at this diagram, the flit FH B0 and flit header B1 is placed at the end of the 256-byte flit, starting around byte 44. This is also supported for the new management transport protocol. And the format 4 here, it is standard 256-byte start header. This is the counterpart. It's mandatory for CXL 256-byte flit mode, and this is optional for streaming and PCI flit modes. Looking at this diagram, the flit header B0 and B1 is right at the start of the flit at byte 0 and byte 1. This is also supported for management transport protocol. Then this slide shows the common flit header definition for all these 256-byte formats. And the format 5th and 6th is latency optimized 256-byte flits. These formats are also all about wiring the most performance out of the link. And the format 5th is without optional byte, and the format 6th is with optional byte. These are strongly recommended for high performance CXL and streaming protocols. The diagram shows how the fields are rearranged to optimize for latency, and for example, by moving protocol information earlier in the flit, let's briefly cover the other key functions of the adapter layer. First is the CRC. The adapter handles CRC. A 16-bit CRC is computed over 128 bytes of messages. And the second is retry. The UCIe retry mechanism is a simplified version of the one in PCI. For example, all the 10 bits PCIe retry related counters are replaced with 8-bit counters in UCIe. And here is arbitration and muxing. This is a critical function if a die is supporting multiple protocols. The adapter is responsible for arbitration and muxing. The diagram shows different scenarios. The first is single protocol and the second is single CXL stacked with itself has two protocols like CXL IO and CXL cache mem that must be multiplexed. And the third is a complex 2 CXL stack scenarios where the adapter multiplex 4 separate protocol interfaces. This specification defines many valid combinations for this, such as both stack as PCI or both stack as CXL or a mix like PCIe and streaming. So let's now moving down to the physical layer. It supports data rates from 4 up to 64 giga transfer per second. Here the valid framing is defined. A key concept is in the PHY is valid framing. At this time diagram shows a valid signal is used to frame the data. For each 8-bit data packet, the valid is asserted for first 4 UI and then deasserted for 4 UI. And here it is modules. We also see the module definition here. And advanced package module has 64 single-ended data lines. Here you can see that. And while in standard package module has 16 single-ended data lines. This directly related to the cross 64 and cross 16 configuration as we have seen earlier. Now moving to the retimer. Finally, the 5-layer specification includes the retimer. A retimer is used to extend the UCIe connection of package, allowing chip-to-chip communication across a large system. Now moving to the next slide. This is one of the most critical process, link initialization. This is all managed by the physical layer link training state machine, or we can say LTSSM. The high level flow is here. The very first stage is sideband initialization, you can see here, and the second stage is mainband training and parameter exchange on the sideband, and the third stage is protocol parameter exchange. Only after these 3 states are complete, we can transfer the flit. Let's look at the key LTSSM states. The very first is reset. The physical layer must remain in reset for minimum of 4 milliseconds. The second is SB init. The sideband initialization procedure is performed at 800 mega transfer per second. And the MB init here, the mainband is initialized at the lowest speed, that is 4 giga transfer per second. Both dies perform one die calibration and repair. And here it is MB train. In this state, the mainband speed is set to the highest negotiated data rate. This is where the complex die-to-die training happens to the center, the clock with respect to the data. And here the link init. This state is used to exchange adapter and link management messages, and it performs the RDI and FDI bring up also. And the next state is active. This is the final state where transactions are sent and received. Now importantly, UCIe 3.0 introduces key enhancements here. The MB init dot stall. A new mechanism mbinit stall is added in the mbinit param state. This state is used to provide additional init time for the management transport path to be negotiated before the main link training continues. And the runtime recalibration also. This is also a new optional feature called TARR TX adjustment. It allows the transmitter to compensate for signal drift during the active state, which improves reliability without the high latency of a full retrain. So here we have mentioned the sideband, but let's be specific. It is a critical out-of-band channel used for training and register access and link management packet. But the key UCIe 3.0 enhancement is in this slide. The top diagram shows the original sideband packet transmission, which has a required ideal gap for at least 32 UI between packets. You can see here. And the bottom diagram shows the new sideband performant mode PMO. This mode removes that ideal gap, allowing back-to-back packet transmission. This significantly increases the throughput of the sideband channel, which is critical for the new data heavy management features. So now moving to the next slide. Once the PHY is trained, the layer need to handshake. First the RDI bring up is done. So this handshake is done between the physical layer and the adapter layer. Here the diagram shows the flow. The PHY and adapter uses the sideband messages. Like you can see here, link MGMT RDI request active. This message is link management when it send RDI request active to the next die, then this agree to move to the active state. And here it is FDI bring up. After RDI is up, after RDI bring up is done, then we can move to the FDI bring up. This final handshake occurs between the adapter layer and the protocol layer. It's very similar flow using sideband messages to get both sides in sync. After this is complete, the protocol layer can finally start sending flits. The state machines for RDI and FDI are shown in these slides. You can see here. Now moving to the system architecture. Now we get the most significant update in UCIe 3.0, which are all new architectural features. Here is UCIe manageability. This is a new optional mechanism to manage an entire SIP independent of the mainband protocol. As this complex diagram shows, it allows chips to form a management network using management ports and management elements. You can see here. Now moving to the MTP encapsulation. This is how manageability works. It defines how management transport packets MTPs are encapsulated and transported over the existing sideband or mainband links. Now moving to the UCI debug and test architecture. Building on this, UDA provides a standardized debug infrastructure for chips and SIPs. The diagram on this slide shows an ATE automated test equipment can connect to the package and use a DMH within each chiplet to route, debug and test packets. Now moving to the early firmware download. This is another major new optional feature. It allows one management entity to load firmware into the another. This process can be used to download firmware image into a circular buffer. As shown in the state diagram, you can see here, allowing a chiplet to initialize before the main link is active. You can see in this diagram. And here we see some transaction logs and waveforms from our chiplet verification IP showing this protocols in action. This is the streaming row format, and these logs are 68-byte flit format. Here you can see the standard 256-byte flit and for PCI. The next slide is standard 256-byte flits for CXL cache mem and CXL IO. And finally in this slide you can see the latency optimized 256-byte flits. These are great visuals to confirm what the data looks like in the live simulation. So to summarize, UCIe is the fundamental standard for the chiplet ecosystem. We have covered the flexible packaging options for low cost 2D to high performance 2.5D and 3D. We have seen how it scales with multi-module support and ensure reliability with redundant links. And the most important, we have explored the major 3.0 enhancement. that provides a full system architecture for manageability, debug, and firmware loading, which are critical for building complex multi-die systems. Ensuring these interconnects performs as expected through rigorous testing and employing silicon lifecycle management strategies are the key requirements for success in this new ecosystem. Thank you so much for your time and attention.